So are you waiting for something or?
Yeah, it's going live. Yeah, now it is live. Okay, so.
So are you waiting for something or?
No, we are
Yeah,
good.
it's going live. Yeah, now it is live. Okay, so. Are you going to introduce me or?
Yeah, I'm just making sure that this live thing is okay.
Yeah, it probably has a lag. That's why I heard echo. Yeah.
Yeah. Okay, so welcome everyone to the largest chapter in the Silicon Valley section of IEEE. We have over 4,000 subscribers in our mailing list. And we are uniquely positioned by virtue of its location and available expertise. We have a strong following of over 12,300 followers on Twitter alone. So today's talk, today's talk is artificial intelligence for high performance computing. This talk focuses on how artificial intelligence techniques can be used in the development of the high performance computing environment and tools. As larger HPC systems become more and more heterogeneous by adding GPUs and other devices for performance and energy efficiency, they also become more complex to write and optimize the HPC applications for. For instance, both CPU and GPUs have several types of memories and caches that codes need to be optimized for. So this talk, our speaker, Professor Elster, is going to show how artificial intelligence techniques can help us pick among tens of thousands of parameters one ends up needing to optimize for the best possible performance of some given complex applications. Ideas for future opportunities will also be discussed, and Professor Elster was kind enough to talk about the history of computing in Europe, I believe, as well. So that's a bonus for us. Professor Ansi Elster is a professor of high performance computing in computer science at NTNU and was a co-founder and co-director of the Norwegian University of Science and Technology's Computational Center and Visualization Program. She also established the IDI NTNU HPC-Lab, a well-respected research lab in heterogeneous computing that regularly receives international visitors. She's also a visiting scientist at the University of Texas at Austin. Her current research interests are in high-performance parallel computing, focusing on developing good models and tools for heterogeneous computing and parallel software environments. Methods include applying machine learning for code optimization and image processing, and developing parallel scientific codes that interact visually with the users by taking advantage of the powers in modern GPUs. Her novel linear bit reversal algorithm is still noteworthy, has so far supervised over 75 master theses, several of which have received prizes, and has supervised several Ph.D. and postdocs and served on Ph.D. committees internationally, including in Denmark, Italy, Saudi Arabia, Sweden, and United States. She has published widely in the field of high-performance computing. By the way, it is 3 o'clock in the morning, early morning, for Dr. Elster. So we should really thank her for her dedication to the profession and interest in speaking to all of us today. So with that, I will give the control to Professor Elster. But before that, I just wanted to remind you that the links to the video and the slides will be posted on our website in about a week. The recording will also be available on IEEE.tv for you to watch later. And for the questions, please feel free to post them on the chat window, and I'll try to relay them over to Professor Elster. So with that, thanks again, Professor Elster, and it's all over to you.
Thank you. And thank you for inviting me, and thank you out there for coming and watching this talk. I will admit that, yes, I've made it little lower tech than I usually would, given the hour I'm talking at 3 a.m. and also because I'm doing this via video and not in person. I hope that, however, that I spark enough interest, you'll feel like inviting me back so I can actually talk more technical details in the future. So if you're expecting an extremely technical talk today, you'll be a little bit disappointed, but hopefully I'll give you enough information to point you to some new and interesting concepts or new and interesting ideas, or maybe some history you didn't know from before. And you'll also start recognizing some of these things. Of course, in Silicon Valley, you already heard of ARM. I can't imagine you have not heard about the ARM. But you know, this fellow over here and this chip here, you may or may not have heard about. That's actually Fredrik Bull, and that is the MIWO chip. So we'll see how many of you know about those. And hopefully I'll get to talk about all of them. So where will you find me? Well, you'll find me in beautiful Trondheim, Norway. That's where I'm sitting now. And like you said, it's about 3:08 in the morning. So it's actually dark outside since it's the fall. But in the summer, it's pretty much light all year, all day through, or at least kind of dusky, dawny around midnight. In the summer, however, I escaped to University of Texas, and where I've also spent all my sabbaticals and maintain a home there. I also spent 20 years in the States before returning to Norway in 2001. And you can probably tell from my accent, I've been influenced by the US American way of speaking. But I can do a rather good British impersonation for those who prefer that. But since this is given to America, I'll keep my American accent. I cannot do any presentations or talk about my research work without acknowledging the many students I have supervised throughout the years. I guess it's approaching over 80 now. And, you know, those are really the ones who enlighten me, they teach me much more than I teach them. I'm quite sure about that. I call it parallel teaching, right? Because they're gathering information for me and I'm picking them up and we're exchanging ideas. And, you know, it's just a great, it's really what keeps me going, I have to say. That's the big advantage of being in academia, access to a lot of bright new students every year. And also, you know, I would like to acknowledge all my collaborators. And if you want any more Norwegian, I mean, there are actually Norwegians in your part of the world too. In fact, my former student, Fredrik Kjølstad, just joined the CS department at Stanford, you know, which I'm sure you've heard about that school, over, you know, down up the valley. So he's actually now a CS professor there. And here you see him in Norway. So we're very proud of him, of course. And we were also part of, my lab is now also part of this SFI Center for Geophysical Forecasting. And that's basically Research Council Norway sponsors a limited number of centers for research-based innovation. And we received one of those awards. It's an 8-year award. So this program will go on for 8 years since it's begun. We just started. And we have a lot of industrial partners. And the reason I paired with them is because you may or may not know, Norway is quite known for oil and gas explorations. And because of that, we have some of the very top-notch geoscientists working at our university. And although, you know, I like to think of myself as doing good HPC work, there's no question that these people are in a class of their own, and of course, collaborating with the best type of scientists and helping them with HPC just makes me feel that my group gets that much stronger. So and hopefully we'll be able to talk even more about this some other time. I also want to thank two of my collaborators for slides. One was Dr. Maria Giron, who I just had a meeting with today. She's the Chief Technical Officer at the CERN Open Lab in Switzerland, and Dr. Pavel Gepner, who's a Graphcore and at the University of Warsaw. And Graphcore also has a strong link to Norway. So the outline for this talk is, why should you, you're in Silicon Valley. Obviously, that's where everything in computing happens, right? Well, over in Austin, we may, slightly disagree on this, but, Silicon Hills and Silicon Valley, what else is there, right? And why should you listen to European? So I'll talk a little bit, my talk to sort of help you, encourage you to listen to me is talk about which went from Bull to ARM and Atos. I'll mention some of the European exascale initiatives. We'll address some of the benchmarking challenges, but of course, we'll also talk about our experience with Autotuning, and I'll try to move that up earlier in the talk so that you will at least cover that before you sort of drift off. So like I say, why should Silicon Valley engineers listen to Europeans? Little at Norwegian. Well, if I want to be tongue in cheek, I can say that must be bull. And that's like and then ... because you don't want to say bad words. But, contrary to popular belief, computing industry did not start in Silicon Valley. You have a lot of startups, but the computing industry did not start there. It actually all started with a guy called Jacquard, Babbage, you may have heard of him, Lovelace, Hollerith, and not to mention Bull. So in 1804 to 5, which is quite a long time ago, Joseph Marie Jacquard invented the punch cards for weaving looms. So he had these big complicated weaves, weaving machines or looms that we call them that will generate these really awesome patterns. And for that, he basically generated the concept of using punch cards. Now in circa 1830, Charles Babbage did the analytical engine. And I'm sure several of you who've taken computer science history or classes know about that. And of course, the lovely lady Ada Lovelace, which is known as the world's first programmer, again, using punch cards, sort of based on the concept from Jacquard. And she even quoted saying that the analytical engine weaves algebraical patterns, just like the Jacquard loom weaves flowers and leaves. And if you want to read more detailed about this, you can look at this Columbia University website. And if you didn't think these weaves were complicated, it took actually 24,000 of these punch cards to create this honor, in honor of Jacquard, this basically silk weave. So this is actually a picture of a silk weave that was created on this loom using 24,000 punch cards. That's a whole, so just in case you thought you were writing long pieces of code in the Silicon Valley, there were actually people back in the 1820s doing, serious punch card designs for weaves. How's that? I thought that'd be kind of a fun fact for you guys. Now, there's of course a more known computing history from Hollowworth. He worked in the 1880 census after his degree from Columbia engineering degree in 1879. And of course, it was a very cumbersome task doing the census data back then. And he also took a 1-year leave to MIT mechanical engineering in 1882. And then actually did all kinds of other things you may not know about, worked on railroad braking systems and mnemonic, this and that. But then, of course, he got pulled in, and they took, the census back then took about 10-year turnaround. But he took the idea from Jacquard about the punch cards and integrated it with the tabulating and sorting machine he created, that he then first tried paper tape, but really decided punch cards were better, and won the competition for the 1819 census that reduced it, basically that 10-year job. And depending on who you talk to, somebody say with 6 weeks, some would say 3 months, some 3 years. You have to sort of look up the references. I'm not going to try to dispute various historians. But the point is, he created this sort of what's known as the first computing machine, as you see a picture of here. It basically led to his PhD from Columbia, and also a very well-known patent that it was filed in, it says January 8, 1989. Of course, it was 1899, so that my bad on that one. Sorry, I guess some of the things go a little fast. Now, in 1911, his company merged with 3 others and became CTR, or the Computing, Tabulating, Recording Company. And that was actually the precursor to IBM, which is International Business Machines Corporation, that took its name in 1924. And again, you can find out more details from the Columbia website. Now, notice the time that Hollerith did his machine. So in 1890s, which was really the same, the first users or adopters of computers, Norway also used the Hollerith machine or tabulator sorting machine for census data. And then in 1917, a big Norwegian insurer known as Storebrand sent his engineers, known as Fredrik Rosinger Bull, to Sweden to study this Hollerith machine to see if they could use it on insurance stuff. And right there, Rosinger Bull decided he could do something that was even better. He wasn't very, not impressed enough with Hollerith. So in 1919, he actually got a patent on an automatic registration machine for statistics and similar purposes. So, it is a bit later than the Hollerith bit, but he sort of outcompeted him, if you wish. In fact, from 22 to 25, he sold 14 of these machines through contracts with a company in Norway known as Oka, led by his classmate Reidar Knudsen. And because he was in an insurance business, of course, they mainly sold to insurance companies. Now, in 1924, Norway's Statistical Bureau replaced its Hollerith with the improved Bull model. So that was for census, and that was sort of, that's why Bull was Hollerith's first real competitor. And like I say, the same year is when Hollerith's company was renamed as the IBM company we know today. And I think this is a little bit interesting piece of history. Now, there was a sad story to this. In 1925, he was in his 40s, Bull dies of cancer. And the company is taken over by Reidar's brother, Knut Andreas Knudsen, who then moved his production to Switzerland and later France. In 1930, he got some accolades at the Paris Fair for office machines. In 1931, it was reestablished as Egli Bull, and then later renamed a couple of years later to Compagnie des Machines Bull, or CMB. Now in 1964, 6% was taken over by General Electric, and the rest was owned by the French government, because they didn't want the US to get a hold of their machines that were doing calculations on their nuclear arsenal. So, that's why it was sort of split a little bit. And then that computer division of GE became Honeywell Inc. and later Honeywell Bull. And so that's part of that history. Now in the 70s, this also was renamed and merged in with the former spin-off. It's the CIHB. And then in 1882, the French took everything back and then renamed it Compagnie des Machines Bull, or Bull SA as it's known. Now, it's like any computer company, and you can look at it just about any major company in the Valley. So there's a lot of mergers and acquisitions. And so Bull acquired 42.5% of the old Honeywell's computing business, and then NEC bought 15% and added another 22.6%. And then basically formed this Bull HN information system. And then this group, which then bought the Zenith data systems in the States in 1989. And then they actually got merged together by Bull buying out that Bull HN into the basically group Bull in 1991. It was actually privatized in 95. And you can sort of see these privatizations and the run for the government goes with the wave of they made sometimes good decisions, sometimes bad decisions. But I guess the bottom line now is that in 2014, they were acquired by Atos. And the Bull name actually still lives on in the computing industry, especially in HPC, when you look at the Atos Bull Sequina supercomputer. And here's a reference for where you want to read about that. Atos itself was, of course, another formed by mergers and acquisitions. So it was merged by two French IT companies, combined with the Dutch-based Origin BV. And then in 2000, Atos Origin was established. It was acquired then KPMG and acquired also Schlumberger Sima, which was this smart car division that we had in Austin. And I say we because I used to work at Schlumberger. And then Siemens IT buy them out at was also a buyout at 850 million euros. And in, of course, 2014, like I just mentioned, they got a controlling stakes, the Bull SA company. And so that's where you see the Bull Sequina machines now are actually part of Atos. I see we have two questions. Are those or just comments?
Yeah, they are just comments. You can go ahead. I'll let you know if there is any question. Yeah.
Sure. So, you know, the rest of the story is that, you know, they also got in August 2014, they got a controlling stakes of their Xerox IT outsourcing business for what a little over $1 billion. They acquired Syntel for 3.4 billion. And in 2020, they inaugurated the Jülich supercomputer Jewel, which is Europe's largest supercomputer, and Jülich, sitting in Jülich near Aachen, Germany. It's now a very multinational company, maybe not super big by the biggest companies in the US, but it still operates in 73 countries, has 110,000 employees, and a revenue in about 11.6 billion. They did actually propose to buy another conglomerate, the GXC Technology, earlier this year, but that fell through as far as I know. And of course, you can read more about the Bull company online. Now, they actually are also an integral part of many of, especially the deeper, but also, which is where the Jülich is part of, and of course are part of many of these European project programs that date back to our previous group of programs that came out with Framework 7 in the European Commission. And you can see a nice report of what was done in these various programs at this URL that I'm showing below, for those of you who are interested in, in the HPC side. And if those of you know me, you know that I'm more known for HPC than AI. I mean, I'm not the AI person. I use AI as a tool for HPC. And these projects here generate from, the collaborative research into exascale software and tools, into the deeper, which is the entry platforms that tries to, build up towards exascale, including the Jülich supercomputer. Now we also are just getting online the Lumi supercomputer in Finland, run by the CSC there. That is actually an HP Enterprises machine, but with AMD processors and AMD GPUs. But we're very excited to be getting access to that one. There's also, of course, had a program on exascale programming models, Mont Blanc, which was, and you'll see a lot of European tech companies focusing on energy efficiency, especially on the chip side, how to generate more energy efficient compute. And I'll say Europe tends to be as far ahead as anyone on that area. And they had a couple of others that maybe not be so focused in the US. But like I say, you can also see the current exascale project at this site. And of course, the big current initiative that came through the Horizon 2020 is the XDICI, or European Extreme Data and Computing Initiative, which is a joint PRACE, which is the supercomputing access to our central resources, and the ETP4 HPC action. And you can also read about that on these websites that I just am pointing you to. Are there any more questions about these? Oh, what's going on? Oh.
Not yet.
What's happening? Maybe it's just slow. Oh, maybe I pressed on it. I'm sorry. So what is, basically AI for HPC versus HPC for AI? So Nvidia, of course, is a very well-known company in HPC. Now, they started, of course, as a graphics company targeting, a lot of them computer gamers, and, a lot of people have Nvidia cards in either their built into their laptops, or actually have bigger cards plugged into their workstation to do, nicely beautiful graphics associated with gaming. And that actually drove a bit business, so that people put a lot of effort into designing the new chips, maybe even more so than CPU, because, mass consumer products are, a very big impact. And of course, these days you find GPUs in, everything from smartwatches to your cell phones to everything else that likes to show you nice graphics. They're maybe smaller, they may be larger, but they're definitely there. But how can AI help HPC? So if you have a big box that's really meant for AI, like this GGX2 that we got back in December 2018, how can we use that to help us with HPC? And you can see it, just looking at the system, you can tell it's not that trivial to program, and it has a lot of complexity, right? And it has these 8 A100, the newest, we have one with 16 B100s, the newest one has 8 A100s. It's a substantial system, has 640 gigabytes of total memory, has a bunch of, high-end switches that are faster than InfiniBand. And then of course, it also has some Mellanox interface cards, as well as, the CPU itself, being, substantially, a nice system. Of course, we have a lot more cores on the graphics cards, where today typically have over 5,000 cores. And then of course, you have quite a bit of a memory. I mean, when I did my Ph.D. at Cornell, I was so happy to have a total of 1 gigabyte of memory on a Kendall Square research machine that I had to have 128 processors to get the full aggregate 1 gigabyte of memory. Now, if you have an iWatch 6, you have the same amount of memory on your watch. So you can see the life has been changing a few, a bit the last several years. And so I can see my background goes back, in fact, even further than that, when I did concurrent parallel Pascal. But like I say, on the KSR, we were really happy to, really happy to get that 1 gigabyte of memory. But of course, the things with heterogeneous computing really started changing when the GPUs became more programmable. And that was about the mid to around 2006, when you saw, CUDA programming environment, and also you got a little higher up from close to the metal on the AMD side. This was also the same year I was part of, or in charge of, getting the new, quote, supercomputer at, I have to put it in quotes now, at NTNU. We're very proud to have this NORD system, which really only had 7 teraflops, but that was considered a lot back then. So it tells you how quickly things change over the years. Now, of course, you could even get 97 gigaflops on the small Almali GPU that you can have on a pad or just a small tablet. These ones have actually 7 to 24 cores, and these are embedded systems. Forget, these are not even in your laptop, right? So you can see the big push. Now, how do we program for performance? So, because if we're going to figure out how to auto-tune and use machine learning for this, we really need to know what is it that matters when you try to program for performance. Well, I'd say the number one thing is to keep that memory hierarchy on your side. So you need to first get the most out of your fastest memory. And the fastest memory you have is your registers. And of course, to help your registers, you're going to be using caching, probably several levels of cache, especially if you're on an Intel, you have 3 levels of cache just on the CPU. And you also will, as much as possible, reduce memory access. You can maybe use your GPU as a compressor, compress the data as you load it in from disk, compress it, uncompress it. Of course, if you want to do it fast enough, you probably have to have some kind of lossy compression, but maybe that's okay if you, for instance, doing seismic data And there are some things, your sort of kind of compressions you can use, like a code with, based on cosine transforms or something that still will maintain the data that you like to see. You also need to move compute to data, maybe. If you have a really big system that generates a lot of data, and I'll mention what Saturn does later, or you have to reduce the data. I mean, these days you have a lot of sensors out there on which is known as edge computing, and we're trying to get the data back. Well, the lines are very slow over, yes, we're getting 5G, but it's still pretty slow. You can't expect 5G everywhere. So you try to do some pre-processing on the edge to reduce the amount of data before you can compute. Now, if you can also, with the really big data sets, before you upload them through the tiers, like we do at Sun, you may also want to do some AI pruning, use AI technique for prunings, and we'll mention more about that.
So, and there's a question on the chat window. What is auto-tune?
So auto-tuning is how to automatically tune or make your program performing better, given presumably your memory hierarchy. So, instead of just like you did in the olden days, your program were auto-tuned from version to version, because basically before 2005, you ran your program, you bought an X computers, you just ran the computer, you ran your program again, and it ran faster because your clock was faster. These days, when you actually upgrade your computer, it's not as easy as just recompiling your code, because your memory and hierarchy and your memory structure and the number of cores you have may have changed. So that you have to do a lot of hand coding and hand tweaking. And auto-tuning tries to help you avoid that and let the help you tune or optimize your code for you. You see these sort of auto-tuning techniques in frameworks such as basic linear algebra programs, or BLAS, or certain libraries like the FFTW library, where you try to it will actually, when you install it, the library will auto-tune or try to adjust how it subdivides its problems, or does a divide and conquer of the algorithm, and optimizes it for the cache levels. And so rather than you trying to tweak and hand code your FFT, you will call this library, then hopefully will auto-tune it for you. And that it will be the case. They'll do a planning stage and they will adjust it for your particular computer. And hopefully then you'll have presumably have a very fast implementation of the FFT, then you can use this part of your program. And the same goes for like matrix multiply, and a few other codes.
Again, one other question I had was, how does the ARM GPU compare with other GPUs? Which GPU? Sorry, I didn't hear you. The ARM GPU, how does it compare with, say, the Nvidia ones?
Which one when he was? Sorry, I can't hear what the first board you're saying. Maybe I don't know that GPU. Are you talking about
in the previous slide?
Okay.
You said that previous, I think. Yeah.
Oh, the Mali GPU?
Yeah, the Mali GPU.
Oh, the Mali GPU, the ARM GPU. So all ARM GPUs are very small. They're for embedded systems. They're not big compute. I mean, an Nvidia GPU, even several years ago, will be several teraflops. This one has gigaflops, so obviously the order of factor of 1,000. But this is something tiny bit you have in a small embedded device like a mobile phone compared to what you'll have on a supercomputer. So you have, but things are changing, right? Now we have an ARM-based supercomputer, and they are growing into that space of at least Nvidia has sort of made more embedded GPUs, and then ARM has expanded their embedded GPUs. So there are definitely some overlapping in some areas, like for robotics and autonomous vehicles and things like that. Sensors for those kinds of things. I'm not going to say which one is better. It really depends on the application.
So the Mali GPU is mostly used for edge computing and stuff like that?
Yes, it's for embedded. You'll find it in your smartphones. You'll find it in your watches, et cetera, et cetera.
Okay, thank you.
And finally, computer science education has, of course, not gone out a window. We still need to pick the right algorithm, right? I mean, you probably were taught that the reason you want to use an FFT as a fast Fourier transform rather than just a Fourier transform, it's of course it's n log n, not n squared, right? And that matters when the data is big. And we're only getting bigger and bigger data. So of course it's important to pick the right algorithm. And if you can't remember anything else about performance, you'll just have to remember it's like real estate. It's all about location. It's like the feed a parallel course fast enough, we get the location of the data, move the compute to the data or reduce it. That's about location of the data. And pick the right algorithm that addresses the data distribution is also about location. And of course, I've given this talk abroad, so I also like to, as you can see, I've added the French and the Italian version. I probably should have had a Spanish version also for people in Silicon Valley, but hopefully between the French and the Italian, you can probably deduct the Spanish version. How's that? So my group tries to really focus on how can we use auto-tuning using machine learning. So how can we optimize codes automatically for programmers? If you write one program in a certain way, and then you want to move it from one platform, especially for graphics cards that tend to come new ones every 6 months. So it's a lot to have to recode your applications every 6 months. Let's just, in practice, it doesn't happen, right? So we want to try to generate tools for how to auto-tune and use some of these machine learning techniques from the AI space, right? And so I'm only going to talk about AI as far as machine learning. I mean, AI is a big field that can include a lot of other things, but that's the only one I'm talking about. We also are benchmarking some graph algorithms and frameworks because graph algorithms are also tightly coupled with AI. We've also been benchmarking AI frameworks with Saturn. We're, of course, doing some geophysical modeling on GPUs with our new center. And actually, for the big data we get from those geophysical modelings, again, we have a lot of sensors out there that read a lot of data. And again, not me personally, but my colleagues are looking at AI techniques, and that probably will be a big part of that eventually. And then we also have done some other interesting projects. But the biggest the biggest recommendation I can give to you, if you're trying to program, on high performance computers and trying to do AI, is that you use the libraries. You want to use either the IBM's MKL or Atlas or this QBLAS. You really want to use, you don't want to write a triple for loop yourself. And I'll show you in the next slide why that is a bad idea. It really makes a huge difference if you can cast your problems into something that can use libraries already there. That goes also for the FFTW. There are some maybe not as optimized libraries, and it could be better, like PETSI, which has a conjugate gradient method, SOR, how to solve partial differential equations. And of course, Nvidia and others have CUDA libraries, and they now include, CU and N. So, if you can use, the libraries, you'll be a lot better. The questions or?
Yeah, there is a question actually. There are actually two. So the first is ARM will perhaps be more app specific versus GPU for other computational solutions, as ARM consumes much more power. Comments on ARM outperforming GPUs in tensor applications? So, ARM is, and I'll talk a little bit more about ARM, but ARM has two components, actually. There's the ARM CPU and the ARM GPU. And the GPU is actually designed here in Trondheim, and it's the Mali processor I was talking to you about. And they were just as low powered, if not lower powered than NVIDIA cores. Whereas the ARM CPU, you're right, it does compute per core.
use more energy because it's a general CPU, not the special, not the very reduced instruction set, you know, graphics core.
Okay, and the other question is, with artificial intelligence, can one predict snow avalanches accurately?
No, I wish, not yet. In fact, we have trouble even writing the physics for it, right? So we are looking at, you know, physical models, and we hope to add some AI to it. But, you know, weather forecasting, including avalanches, very, very challenges. And so what we are adopting is some of the using sensor data for, you know, from and trying to not pick up more data from actual avalanches, you know, whether it be mudslides or snow. And so we can model them better. And then, and hopefully down the road, apply AI techniques and really get them going, but we're not there yet.
Okay, I think that answers the question.
So, like I said, we were the part of this consortium for geophysical forecasting, which I just mentioned. And we also have several other collaborators, including Saturn and Graphcore, like I mentioned, also other people at NTNU and elsewhere. And also the two big applications in Norway, I would say, for HPC and also for AI will be medical, you know, how to do medical interpretation of images. And they have a lot in common with seismic imaging, you know, where we try to look at seismic images. So there's a lot of overlap, at least from the computer science side of those two areas. And as you know, Nvidia doesn't even sell itself as a graphics company anymore. They sell themselves as a AI and AI IoT company, right? So though they started their first GPU back in 1999, started presenting with a CUDA, and we actually started that same, our first GPU impact back in 2006 when one of my students did a wavelength transform on a cardiac ultrasound scanner that, you know, sped up the computation 40 times. And so that now, of course, any ultrasound scanner from Siemens or whoever will basically be using GPUs, right? And of course, by 2010, maybe not of course to some, because I had to argue with that in 2007 for supercomputing. I was on a tutorial committee, and CUDA Nvidia wanted to give a CUDA tutorial, and there was some skepticism why we should let this gaming company come and give a talk and at supercomputing. But I pointed out it was, you know, had a lot of potential for future. And by 2010, you see them being dominant. You know, a lot of the top 10 supercomputers or biggest, largest computers in the world do indeed use GPUs for acceleration. And of course, the GPUs at Nvidia these days is really targeted AI. And you see a lot of other companies pop up, like Graphcore with the IPU that also targets AI applications. And as you know, being in Silicon Valley, AI is a pretty hot topic. So this is some of the mentions of those projects. We did that back in 2006. Now, what we're currently looking at is more of the Autotuning. So one of the little projects that my PhD student and former PhD student, current PhD student, and former PhD student did was Autotuning benchmark techniques, where they looked at the roofline model case. And that was, you know, presented recently at a workshop. And the motivation here is that scheduling and hardware selection, we want to model the performance of the architecture. And then we use the roofline model to compare the systems, because when you get a new system, you want to kind of get an idea of how well it performs. You can get the theoretical peak from the vendors, but the practical peak performance is often far lower. So how much, you know, compute, or how good will my program work on a given on the given system when I just get it? And then you want to find this peak practical performance through auto-tuning benchmarks. So if you have some benchmarks you can run that can auto-tune for you, you may get a good sense for how good your other applications will, including your AI applications, will be on that system. And we first used machine learning techniques in one of our first papers in 2015, when we did machine learning based auto-tuning for enhanced OpenCL, which is the more generic programming language, if you wish, for GPUs, also often used on AMD processors. And we really did a good, we really found some good, basically we had to parameterize that code, and then it was up to the auto-tuner to figure out how to get a good parameterized versions. And our model achieved a mean relative error as low as 6.1%, which is pretty good, and was able to find configuration as little as 1.3% worse than the global minimum, which is really what you get for very hard hand-tuned codes. So that's a really good choice. But they will also have to say that not all of our successes were as successful, and I'll get a little bit back to that. Now, recently, in fact, just today, we a paper based on this benchmark suite for auto-tuners we created, because one thing is there are actually several frameworks out there that will auto-tune some codes, and it's very hard, however, to figure out how good they work. And so we have now put together a benchmark suite for these auto-tuners. We put it out there, and we'll open it up to the public. And like I say, it says in review here, but it actually got accepted today, or earlier today. And so here we parameterized the CUDA program and kernels from the Scalable Heterogeneous Computing benchmark, or known as SHOCK benchmark. It contains 9 different HPC benchmarks that are modified to suit the different several auto-tuners. And it also includes a command line interface. We tested both the 4 we feel like are the major ones: the Open Tuner, the Kernel Tuner, the CL Tune, and KTT. And if you don't know about auto tuning, you can look at all of those and see what they can do for you. And we, of course, used our DGX2, but in addition, we have 2 nodes of IBM Power System AC922, which is actually the same basic hardware as it's in the biggest computer in the US, known as Summit. Now they have 6 Tesla water, specially cooled Tesla cards on each node. We only have 2 on one node and 4 on the other, but at least gives us a good a system to test, because it's for my group only, so we don't have to share it with anyone, so we can do actually real benchmarking. The problem with production system is they're time shared, so it's hard to do benchmarking. Yeah, we also have a system with the 20 Tesla T4 GPUs that we actually most of the time use for teaching, but off semester can do some benchmarking on. So the Rufal model case study, I got these out of, I see I got them out of order. You want to be able to have, we were able to get us basically a big search time improvement from the auto-tuning benchmark with up to 116 times. And the general auto-tune management techniques can then be applied to any auto-tuning application. And the idea was here to stop once you've auto-tuned and gone well enough, you want to be able to stop in time. And that's some of the interesting techniques we use to get that, to achieve that. A more sort of AI for HPC that's at the core, and I could spend a good portion of a talk just talking about this, and the follow-up paper that we also accepted today is that when we want to use auto-tuning on CUDA codes. So I had a student last year download all of the CUDA code that was open and runnable he could find on GitHub. So that was quite a big data set. And then he cleaned it up and parameterized it, and has then since done some AI ML techniques for how to optimize, for instance, for the block size. So that's like the deep learning and NLP models. And yes.
So, Anne, just a question. Basically, you take the code from GitHub and CUDA code, and then use some NLP techniques on it?
Yeah, so what we do is, you need to have it parameterized. So first you need to find the code, then you need to make sure they have a make script that actually runs and works. So was our basic, because I can't have my students look at every single code on GitHub and fix the codes, fix the bugs. That's not going to happen. So they have to be runnable. And then we try to clean them up some, and then parameterize them. And no, I guess I didn't include a lot of that. You can look at that paper if you want to look in detail. But what we're doing is we parameterized it for the block size, and then and this data set is out there. We making it open, and we're doing some collaborations with hopefully Greece and other people, and then we'll also include more codes into this LSCAT database, so we can do more interesting auto-tuning as we expand it. And so the idea is, like, rather than doing a brute force search over all the codes, you try to find a big model that can help you using machine learning to optimize the rest of them.
Just curious, what would be the parameters here for the code? You're saying parameterized.
Yes. So for instance, the block size for CUDA codes is probably the number one we checked, is the one we already checked. And there are several other checked. I didn't include those slides here, but when you're looking at what kind of memory, whether you, are you going to be using shared, how much shared memory? Now, we didn't do this all for our data set yet, but the other parameters you typically see is how you use the different kinds of memories on the GPU, because that will impact your performance.
So it does go into the code itself then? Yes.
Yeah. I mean, the LSCAT definitely has it parameterized for block size, and then for other, if you really want to auto-tune, like we did for like Thomas Falk did, he did also look at others. But yeah, you have to look at you have to parameterize, the codes have to be parameterized, otherwise they can't auto-tune.
Okay, so basically
we don't do magic.
Yeah. So you basically extract the features and then apply artificial neural networks, or is there any other deep learning framework that you apply?
Yeah, so so far we've just been using straight CNN, nothing fancier than that. But we'll see what else we'll do next. Yeah.
Oh, so you applied CNN on the extracted features?
Yes.
Okay. Okay, there's a question on the chat window. It reads, reproducibility in HPC, an ongoing opportunity. Did you rerun benchmarks or explore reproducibility from a gauge perspective?
Yes, in fact, this is was the big thing with the roofline case, is to do a lot of experiments and we'll show a lot of interest in. We have a student who have really looking, especially for auto-tuning, how you can do reducibility and how you even test the codes. And so all of our codes, have been run several times to verify. Of course, there are some, any kind of ML is a little bit black box, and so you have, but in general, we get more or less the same result each time. There are, of course, sometimes you don't succeed. So I want to mention that before I get cut off. There was a master's thesis a couple of years ago when I had Dr. Gavin Taylor, who's at University of Maryland and the US Naval Academy, visiting for 16 months. He came to my lab to learn more about HPC, since he's responsible for HPC at the US Naval Academy. And the nice thing for us, he could teach us a lot more about machine learning, and he does a lot of the area of reinforcement learning. And we tried to look at basically the whole standard toolkit or SDK from Nvidia and the compiler flags, because as you know, those who've been looking at, there are so many compiler flags you can set, on a given application, right? And can we train a neural network to predict how compiler optimization settings can impact the execution speed on untested programs? And we tested the SDK on various flags, but it wasn't as successful as we hoped. Probably because the data set was too similar. There was, you have to have some variation. But it was, of course, a very good, educational experience for the student. Who's now has a successful career at Microsoft. But I'm just saying that that they basically, AI doesn't solve everything. And one of the big challenges in this field is just like for design engineering, it's an old problem. It's not just for AI, it's for design engineering. Is when you get an outlier. Now, is this outlier something that is really interesting? Like if you have an autonomous vehicle and you see something unexpected happen, is this like suddenly a kid coming out of nowhere that you really shouldn't be hitting? Or is this just some kind of data that's just a glitch you can ignore? And that's just a really hard, it's just a really hard problem, right? And it's not necessarily something you can easily get around. And people are working on it, and it probably will be on a domain basis, right? And the more questions, is that what I'm seeing, or?
Yeah, there's one question. So which of the 4 auto tuners you tested do you think is best? That's the question from Dave.
Oh, well, I guess good question. They're good for different data sets, or different for the different applications. And I guess you can go and read this paper which now is being published, and for which sets they are. So there's not one answer to that one. I now have sort of summarized. I don't know if you want to. I always want to say a little bit more about some processor technology in Europe, or if you want to have some more questions. I mean, it's up to you.
There are no questions as of now, so you can go ahead, I think.
So here I've now borrowed some slides from my partners. So one of the European companies known as Graphcore, they have really been targeting their graphics cards, or accelerator cards. You'll find them in Dell systems. Dell servers can be shipped with Graphcore cards. And they have this system called the little designed IPU that are claiming great breakthroughs from AI point of view, right, for AI workloads. And so they basically have this data generation, you model and design your ML training, and then you have the model inference with a solver. And you, instead of having the classical HPC simulation, you'll be aiding your HPC simulation by having this accelerated part with a sort of an AI tunable way to help your applications. So whether you plan, you try to adapt your program, or help your, for instance, the CFD simulator with also adding this AI component. And there's already shown that AI can help a lot of AI applications, including high energy physics, known as HEP. And you hear CERN people call HEP, says HEP, HEP, HEP. That means high energy physics. CFD, which is computational fluid dynamics, and your avalanches can be done with the computational fluid dynamics, partial differential equation, protein folding, Monte Carlo simulations, which of course are nice for parallel computing because there's so lots of separate instances, and of course the very, very complex, which we still haven't completely solved, right, is weather forecasting. You can never get a good enough weather forecast, and of course oil and gas explorations.
So, and there's a question in the chat window again from Dave.
Okay.
He's asking, when what you want to do is not in a library, other than programming in CUDA, what do you think is the easiest way to program an Nvidia GPU?
So they have so there are now, for instance, and depends on, of course, if you are you on the Nvidia GPUs to begin with. Now we have, for instance, the AMD cards coming out for our supercomputing Lumi, and there they have a framework called HIP that sits on top of OpenCL and CUDA. And so maybe you want to start with HIP, and you can Google that. And if you Google that together with it's like a higher level language that's supposed to be a little bit easier than going directly into CUDA or OpenCL. How's that for an answer? There's also, some other frameworks that more just CUDA specific, like Thrust. But anyway, I think because of the future, and I like to have platform independent programming, I think you should learn HIP. How's that?
Yeah, sounds good.
So just want to say there are lots of different kinds of applications, HPC applications. You can have use these AI accelerators. You can see they use AI for turbulent boundary layers, for wind farm layouts, for data-driven models in reactive flows, for when you're designing aircrafts, and folds, and also for wetting and hydrodynamics. And again, you see Atos popping up here as part of their, the European ecosystem. And of course, you see this hybridization. So, you're going to be having not just an HPC workload, but you're going to have a mix of an HPC and AI workload where you try to, for instance, use AI to read the prune the data, or AI to do part of the simulation, but combine it with more classical ones. So you're going to have some CPUs and GPUs, and may also have this special AI accelerator in combination with it. Now, one area where you see a lot of data, and also the center that has a lot more AI coming in their plans is the CERN, the Center for European Research in Nuclear, as they say, if you said, or nuclear research, right, in Switzerland. And this is, the big high energy physics experiment we have here. It crosses, it's tried to look at, what are the secrets of the Big Bang. They have, a huge, they have huge amounts of data, like petabytes of data. And they're really doing these sort of classical high energy physics experiments. And it's a huge facility that spans actually 2 countries. The actual loop for the CERN colliders are spinning around between Switzerland and France. So it's known as the most powerful discovery machine. It's the Large Hadron Collider. It's, of course, they are basically traveling at the speed of light, or very close. So they run 11,250 turns every second. So obviously, if you're going to trace such things, you're going to generate a heck of a lot of data. And so sure enough, they generate about a petabyte of data per second. So obviously, they can never have enough storage, never have enough compute to do all their stuff. And that's sort of their motivation. And as you know, may or may not know, CERN is also where Tim Berners-Lee basically wrote the first web application, right? The web browser to access documents at CERN. So it's known not only for their particle physics, but being quite inventive on the computing sides as well. And as you can see, they have quite a bit of software. They have 50 million lines of code, mostly written in C++ and Python, as thousands of scientists that have contributed to this. But a lot of the code is over 20 years old, like many old sites. You see the same thing at the DOE sites in the US, right? They, of course, have a big compute, and they have access to over 1 million CPU cores and exabytes of storage. So this is a huge compute challenge. And in the middle of this, of course, it's HPC between adopting the ML techniques. And of course, they also are adopting GPUs or a heterogeneous computer. I know they have a lot of GPU. They have actually together with, in a collaboration with Flatiron, have access to A100s, also with Jülich, and also some FPGAs, field programming of gate arrays, the special purpose hardware that gets tuned to a given algorithm. And they have a lot of challenges to do this. And we'll be indeed looking at AI and ML techniques to help them. And the big challenges there are like, it's everywhere. It's like the software and architectures, so, supercomputers, if you need a lot of compute, you're going to need to adapt to the best in architectures, which tend to be heterogeneous, include accelerators like GPUs. You're going to need to have to figure out how you do benchmarking and accounting, especially on the benchmarking side is where we've been collaborating with them, because just benchmarking these AI applications or HPC applications is, and how you do it well is actually tricky. There's enormous data volumes to stage, process, and export. They have to use AI techniques for pruning, and they have to use AI techniques to look at the data, and so on and so on. And of course, you probably should be using AI techniques also for strict cybersecurity. So yeah, there are a lot of challenges that they address, and these are the main ones we're working with them on, like I mentioned. And as you can see, my lab is here now featured on the slide she presented at the Euro HPC forum. And there's lots of other, you see American companies like Intel and IBM also being a big part of this. And as far as the processor initiative, there's also a whole array of processor companies in Europe, including Atos and Jülich, but companies like Clara and like I see Graphcore and others are part of this consortium. And to just give you a final rundown, I want to take you back to ARM. Now, ARM was founded as Advanced RISC Machines in Cambridge back in 1990, and was a joint venture between Acorn, Apple, and a company known as VLSI Technologies. VLSI was later bought by Philips for $1 billion, and is, of course, now part of the spin-off of the NXP Semiconductor. Now, in 2016, ARM was bought by SoftBank Group, which is a Japanese conglomerate. And then in this September last year, Nvidia announced it wanted to buy ARM, but that has sort of been stopped both on the Chinese side because the Chinese ARM branch doesn't want ARM buying it, but also there are other, as of course, some monopoly issues too. So that has not been finalized as far as I know. Now, my laptop here is a fairly new MacBook Air, and it actually has an M1 processor, and the M1 processor is indeed based on the ARM IP, because ARM doesn't actually produce any silicon themselves. They only produce a design for a microprocessor, and it's IP. So you sell it. They sell its design and proper rights, and have an ecosystem, of course, around it. The same thing happens on the very embedded side with Microchip, or it also consumed Atmel. Now they themselves acquired dozens of smaller IT companies, and including one known as Phalanx Microsystem, which was a spin-off from my university here in Trondheim. And this Phalanx Microsystem became ARM Norway, and now is the ARM Mali processor design facility that actually here in Trondheim. And if you look at what this Mali processor does, and here you get a little bit more detail than I was able to just rattle off the top of my head earlier, especially given now it's soon 4 in the morning. It first one that came in 2005 had a very fixed functional pipeline. Then in 2007, they added shader cores and had about a 8 kilobyte L2 cache. Now the Valhall from 2020 last year is basically a superscalar engine, has a unified memory, has 7 to 27 shader cores, and uses 5 nanometer fab. And it has from 0.5 gig to 2 gig of L2 memory and 97 gigaflops, which is pretty amazing for such a tiny embedded chip. This is actually now you can find on the Samsung Enos tablets. And you also ARM, in addition to the general CPU, also has, they also do Mali video processors that are specialized for also in conjunction with the Cortex A77, where you do, special purpose for video processing. Now they were actually a spin-off. There was from formerly known as Nordic. So that was again also a fabless semiconductor company. It was founded here in Trondheim, initially focused on mixed signal applications, ASICs, and that did its first standard product, which was a wireless product on the 433 megahertz ISM band in 1998. Now, then it was renamed Nordic Semi and had its first 2.4 gigahertz product, which you can see is very popular for mobile phones. And the third generation ultra low energy processor was actually incorporated into the ARM Cortex. So you can see these are, there's some cross fertilization here. And in 2018, they got their first LTE product to go with an LTE mobile phones. They also have a low power short range wireless chip known as the NRF 53040, which is a dual core Bluetooth. And they had the first wireless system on a chip with 2 ARM Cortex M33 processor, which could operate as high as 105 Celsius, which is beyond boiling point of water. It runs at 64 megahertz or 128 megahertz clock, has 1 megabyte of flash, and also includes a DSP, digital signal processor. Now, let's see, I'm just trying to see everything here. Now, the Nordic Semiconductor also had a spin-off from them. So that Alfege Bugin and Vega Bolon wrote their master's thesis on the RISC architecture, and they got a job at Nordic. But then Nordic sold the mic control to Atmel, which is where they started, generated company to do. And then that Atmel, so it's not Atbet, but Atmel, sorry. And then deduced this AVR, which was an 8-bit processor. Now, Bogin was one of the founders. He spun off and generated Energy Micro, which is the same year was sold to Silicon Labs and is now at Virtual Things. And then Volon and Gaute Mikribis, the other number 2 and number 3 of the company, they actually founded this Maiwo in 2016, which does chips for touchless HCI. And of course, due to the pandemic, that's become a very popular, or interesting chip, right? And we also have a crazy company called Unio who does battery-free processors. I really don't know much about this company. It's kind of in the dark still, but it'll be interesting to see what they do. They claim to take energy from the surroundings. And Nordic has actually now at 872 employees, so definitely getting there. But I think it's getting late, at least for me, or maybe early. So I want to end this with saying having fun, and you should look for other interesting characters from Norway in your area, like Fredrik Kjølstad, who I said who's just joined Stanford. There's Magne Risvik, who used to be Yahoo High Tech. He's now, I guess, mostly in Seattle and Norway. And there should be several other Europeans you should be able to learn from. Although I'm sure we learn a whole lot more from you in general, but hey, I got to give that European pitch even in the end. Thank you.
Yeah, that was really insightful. And there's a question from Dave again, and he's asking, what is your opinion of the Julia programming language for high performance computing?
I haven't used it that much myself. I mean, there's some people really like it. I have to maybe, my students haven't convinced me that we really need to use it, but there are some people who really like it. And I think it has a lot. I think we need to see how it develops. I think it's very interesting. I will admit that my group mostly programs in C and C++, so for the time being. Of course, it probably is because we keep changing architecture so much, and compilers don't quite keep up, right? So, but I think it's worth a close look.
Okay, but for your AI programs, for the deep learning stuff, I think you must be using Python, right?
Yeah, yes.
Okay. So in addition to the deep learning,
you can write Python scripts, right, to initialize stuff. Now, of course, you don't want to write any kind of, like I told you, showed you that slide from MIT. You don't want to write a triple loop matrix multiply with Python. That will be up to 65,000 slower than if you called a library, right? So that would not be good.
Yeah, of course. So your work is mostly into building the libraries then?
Yeah, so we like to build libraries and compiling tools for HPC.
Okay, so libraries, compilers, and auto-tuners.
Yes, Autotuners.
Okay, there's another question. What is your opinion of Intel's GPUs and their data parallel C++ language?
Good question. Still, they haven't, we haven't had a chance to test them enough and find out enough what they are. Of course, Intel is a big company with a lot of brain power, and they do a lot of good things. They have a lot of good people. I know some of the people who work in that group. They certainly have a nice analyzer known as VTune. It's not part of their overall package that we use for many years. We haven't had the chance to really analyze the new Intel GPUs. So I don't know if maybe I can answer that better next year.
Yeah, we'll probably call you back, at least for that answer. So there are a few viewers on YouTube also, but I don't see any questions from them. Yeah. So I think it is already really late for you, or early morning for you. So I will probably.
Yes, 4:15, I guess. Or 4:17.
Yeah, that was really.
So pardon me if I don't answer my questions very well.
No, it was really insightful. Yeah, there are a lot of claps on the chat window. So people are liking thank yous and claps. So I think, yeah, it was really very insightful. So I just wanted to share a couple of slides about our future programs.
Of course.
So this is the IEEE Computer Society Silicon Valley chapter. Dayan is our chair, Young Hee is our vice chair, and I am the secretary. Sachin is our treasurer. So on the 26th of October, we have professor from Singapore, Tulika Mitra. She will be talking on embedded heterogeneous computing. So please plan to attend that. I'm pretty sure that will be insightful as well. And then on the 9th of November, there is an Ask Me Anything session with Professor Pedro Domingos. So I'm sure, yeah.
So ask him the hard AI questions.
Yeah, that's right. Okay, there's a hand raised.
Okay.
So you have a question, Randy? Yeah, you can unmute yourself.
I don't mind seeing some faces.
Sorry about that. Hey, I just wanted to share also the Boise section Computer Society has a quantum computing presentation on the 14th. If you're interested, check out the Boise webpage. This will be a third in a series related to quantum computing, and I just wanted to share with my friends in the Santa Clara Valley.
Oh, great. Yeah, that's very interesting. So hopefully we can also get I can get an email about if we can join, because I have a student who's looking into quantum in collaboration with SINTEF in Norway. Mm-hmm.
Yeah, actually last month we did an event on quantum computing as well.
Oh, great.
So that was cryptography. I mean, yeah, quantum computing is really pushing ahead.
Yeah, and with IBM and others, it's we've been it's still we just had a small university in Norway buy a 2 quantum bit computer, and that cost over $50,000. So I think it's still not something you'll see in your laptop anytime soon, but it's very interesting.
Yeah. Yeah, so I think, so there's another question. Do you think Apple's ARM, do you think Apple's ARM desktops and laptops will be successful?
From a technological point of view, I don't see why not. I mean, after all, I think the Intel, Apple laptops are quite successful already, right? And they have ARM chips in them, really. And of course, you see ARM chips or ARM-based chips in the big supercomputer over in Japan. So they already have some success now. whether they will outperform Intel. Now that's a whole other story. And, there's a lot of other challenges in the chip industry right now, just with, access to fabs and stuff like that. So, yeah, we don't know the end result may not be the pure technical, right? Maybe a supply chain thing.
Yeah. Oh, I should have shared my screen. I was not sharing my screen. Let me share my screen once. And
was that a satisfactory answer, Dave?
Yeah, I guess so. So I will just go over. So on the 9th of November, we have this event, Ask Me Anything session with Professor Pedro Domingos. He is an expert in machine learning. He was interviewed by the Google founders, Eric Schmidt, and his recent book, Master Algorithm, has made some news. So I hope members will take advantage of this event. The questions have been sent a bit early. We said that we'll send the questions by 22nd of October. So if you have any questions, please do send them across. And on the 26th of November, we have Professor Tulika Mitra, who is the Provost Chair Professor of Computer Science and Vice Provost at the National University of Singapore, talking on embedded heterogeneous computing. So hopefully you'll take advantage of these and the future programs as well. So with that, Anne, thanks a lot. It was really very insightful, and hopefully we'll call you back pretty soon for your next talk.
Thank you. And thanks for having me.
Yeah, sure.
Yeah,
right.
I did post the quantum computing in the chat if you're interested.
Oh, okay. Yes, I'll have to grab that before I leave. Let's see. Oh, great. Thank you.
Yeah. Okay, I'll stop the recording here. So thank you everyone for joining on both YouTube and on Zoom. So see you for the next event.
Yes, thank you.
Thank you.
Yeah, sure. Thanks everyone.
Bye.
Thanks, Anne. Have a good day.
Thank you. Bye-bye.
Yeah, bye.
Stop it now.